We will continue with our discussion of lifting line model, Prandtl's lifting line model. Let's go to the full screen mode. Until recently, we've been looking at an elliptically loaded wing. What do we mean by elliptically loaded wing is that the lift distribution, lift per unit span, or lift per foot of span, or lift per meter of span, as you go from wingtip to wingtip, it would look like an elliptical shape as shown in this particular picture. So this is an elliptically loaded wing. So we did some analytical work on that in our previous video. I'll just highlight it. We did some change of variables. Then we solved for the downwash. We found that the downwash was uniform all over the wing. So root to tip, all along the wing, you get a uniform downwash velocity. Then we also found that the induced drag works out to be this number, CL squared divided by pi times the wing aspect ratio. We say that this is the lowest induced drag possible. When we deal with a more general wing that we're going to look at next, you will find it is, we will get a drag that is this thing plus something more. So every other wing other than an elliptically loaded wing will have a higher drag. We also showed that the lift curve slope decreases because of the downwash. For an elliptically loaded wing, this is the formula, but in general for any wing, the lift curve slope dCl d alpha is less than the 2D lift curve slope. So you're always going to generate less lift in 3 dimensions because of the loss of lift near the tip. So the lift starts decreasing as you approach the tip. So it no longer behaves like a 2D airfoil. You're getting a less up lift with a finite 3D wing. And we also found for an elliptically loaded wing, you could analytically write CL versus alpha as a straight line curve, where this alpha I is the induced angle of attack, which is the downwash we talked about, divided by free stream velocity, which is CL over pi aspect ratio. So you could analytically solve many things for the elliptically loaded wing. So this is where Prandtl stopped. Then a person called Glovert in England, Glovert has done a lot of work. We will later on see something called Prandtl-Glovert transformation for compressible flow. He has also developed a theories for modeling propellers. He's a well-known figure in England. Right between the First World War and the 30s, 40s, in that time frame, they had done a lot of work. So we have a computer program called Prandtl.m that I wrote, available at our Canvas site. But we are going to look at the theory behind a more general wing where the wing loading is not necessarily elliptic. So that's what we are going to look at. So the starting point is this equation which Prandtl derived. We had developed it earlier on by looking at one single vortex, looking at how much downwash it produces, which is 1 over 4 pi times d gamma y naught minus y integrated from wingtip to wingtip. This is the downwash. Then we put that downwash, change it into alpha high. Then we set CL equal to A naught times alpha minus alpha naught minus alpha high. Then this is how it came about. So this is the expression. This is the lifting line equation. As we mentioned, this is an integral equation. On the unknown, gamma is buried not only in the outside here, but also inside the integral. So we have to assume some kind of a form or a shape for gamma before we can integrate it. In the previous example, which is the elliptically loaded wing, we assumed the gamma was distributed like an ellipse. So that's what we used. So first thing we do is, just like we did for elliptically loaded wing, we do a change of variable. So one wingtip is at minus b over 2. So cosine theta is 0, 1. Therefore, theta equal to 0 degrees. So one of the wingtips, let's say you're a pilot looking at to your windshield. Then to your left on the left side of the wingtip would be theta equal to 0. If you put theta equal to pi, cosine of pi is minus 1. You already have a minus here. It will become plus b over 2. So pi is the wingtip to the pilot's right side. How about right where the pilot is sitting? There theta naught would be pi over 2. So cosine of 90 degrees is 0. Therefore y naught is 0. So the center of the wing, theta naught is 0. Theta is 0. At one wingtip, theta is 0 and theta naught is 0. At the other wingtip, theta is pi, theta naught is pi. So this is what we mean by the angles vary from 0 to pi as y varies from minus b over 2 to plus b over 2. So we are going to change wherever we see y with this type of a change of variable. Now we also need an expression for gamma. Since this is already in theta, we develop an equation for gamma or assume a solution for gamma in terms of theta. So the solution that we assume is a Fourier series that had terms, only the sine terms, not cosine terms. Why not a cosine term? Let's take a look at the series. So this is what he assumed. He assumed n equal to 1, 3, 5, etc. And he only assumed sine of n theta. He did not assume cosine of n theta. Why is that? Because let's say that he had a cosine of n theta. When theta equal to 0, cosine of n theta is 1. Therefore, you're going to get a finite wing lift at the wingtip. So which is not allowed because at the wingtip, the lift should go to 0. So if you have terms involving cosine of 1 theta, cosine of 2 theta, cosine of 3 theta, any cosine of n theta, you're going to have a finite lift on one side of the wing when theta is 0. How about when theta is pi? Cosine of pi is minus 1, cosine of 2 pi is plus 1, and so forth. Therefore, on the other side of the wing, you're going to have also a non-zero lift at the wingtip. So cosine n theta is bad news. We cannot satisfy 0 lift at the wingtip. That's why Glover did not use cosine theta. Why did he choose only odd numbers? Why not the even numbers? If you plot sine theta from 0 to pi, so let's do that using an Excel program here. I'm going to bring up Excel, so hopefully you can still see my screen. So I'm going to pick several values of pi. Let me make it a little bit bigger screen. So I'm going to put a theta here, and I'm going to find a sine of theta, and I will do sine of 2 times theta, and then I'll do the sine of 3 times theta. This is just for illustration purposes. Okay, so I'm going to look at the 3 potential terms that we can work with. So let me make these columns a little bit bigger. Now theta, we are going to put it in radians rather than in degrees because we are going to have a 0. Then we are going to put a pi. That's 18 degrees. Then we are going to say 2 times that number. You get the idea? Let's go ahead and do it up to 10 times A3. So all I'm doing is now generating a bunch of theta. I'm going to compute sine theta, cosine theta, and then we are going to see what happens. Something is wrong in the formula here. A3 . 4 times A3. Okay, let me do it some other way. So I'm going to add this number to previous number. Therefore, it is A6, A3. So let's copy it for the next several numbers. So what I'm going to do is, I'm sorry, I had to make it $A, $3, so that it's always there. Okay, so I'm going to stop at pi. I don't care beyond pi because we are just going to, I'm sorry, we are going to go so the theta is now going from 0 to pi. So now this is going to be sine of A2. Now copy it. Okay. So it goes, this is the wingtip. When theta is 0 is wingtip. When theta is pi, it's another wingtip. Again, it's very, very small. And when theta equal to 90 degrees, we get the highest value, which is 1. And we see symmetry. That means this number is equal to this number is equal to this number. So the left side of the wing and right side of the wing will have symmetry, same loading. So there won't be any rolling of the wing or the airplane. So it's a good term to keep. So let's look at the sine of 2 times theta. So I'm going to do 2 times A2, it's 0. Now let me copy it. Notice that it's no longer symmetric. So if you have on one side of the wing, you have all positive numbers, 0 to pi. On the other side of the number, you have all negative numbers. That means one side of the wing will be producing, say, positive lift. Other side of the wing is going to produce negative lift. Therefore, the even terms are bad news. You could try this with 4 theta, 6 theta, doesn't matter. So let's try the sine of 3 theta. That's 0. Now we see again we have symmetry. This number is 0.80, this is 0.80, 0.95, this is 0.95, 0.30, 0.30, minus 0.58, minus 0.58. And then in the middle of the wing you get minus 1. So even though it's got a plus and minuses, it's symmetric on both sides. So in general, odd of sine theta is good. Even of sine theta, whether it's a sine 2 theta or sine of 4 theta, doesn't matter. It's a bad news. So we should not use even terms. So returning back to our PowerPoint slides, so this is why Glover picked only the odd terms, 1, 3, 5, 7. He only kept the sine terms. He did not keep the cosine terms. So this is what he did. So we need a d gamma because in the previous slide we have a d gamma over dy times dy. So it's a d gamma is what we are after. So we can take a differential of gamma. Since these are all constants, why do we put a 2? It's just for convenience. Why did we put b and b infinity? Because gamma has a dimensions of distance times velocity. Remember, it's a v dot ds over a closed contour. V is velocity, ds is a distance. So you have a distance in b, velocity here. This is just a convenient factor to get rid of 1/2 and stuff like that that comes, that would otherwise come up. So d gamma is this constant times. You just need to take a derivative of this series term by term. So a typical term will be n times an times cosine of n theta d theta. So that's what the d gamma will become. Now you have y naught minus y, so you have y naught here, you have y here. So you put those things down in here. So this is y naught, y is shown in here. Now, this b and this b will cancel out. 2 will go up there, so it will become 4v infinity times this number. So that's what it would become. So now this term can be taken inside the series. So what we get is, we get taken inside the series. Now, when we integrate from minus b over 2 to plus b over 2, it becomes 0 to pi. By the way, here you have 1 over 4. Here 2 times 2 becomes 4. So 1 over 4 and 4 cancel out. B cancels out. V infinity survives. So V infinity survives. Pi survives. So you get an expression that looks like this. This n times an came from this n times an here. Cosine n theta is in here. Cosine theta minus cosine theta naught is in the denominator. So it turns out you could go to a table of integrals and analytically integrate this expression. So somebody has already done it. Glavert has done it. So the integral of this one is simply sine of n theta by sine of theta. So that's the downwash. Now alpha I is w over v infinity. Remember, w is coming from up to down. V infinity is along the x-axis, so w is along the y-axis. So it becomes a right angle triangle. So the angle between the x-axis and the hypotenuse is what we call alpha I. So alpha I is arctan of w over v infinity, which is just w over v infinity for small radian values of alpha I. So this is the induced angle of attack. We still don't know the ANs, so we cannot numerically compute it. Plus, it's an infinitely long series, so it's got lots of terms. Okay, so we are not sure whether Glavert was right in choosing such a complicated expression, but let's see what happens. So now, if you put for that integral expression what we got in here from this series, and then replace this gamma with this integral, with this series, then group terms together, then this is what you get. You get a system of linear equations for an. Okay. So you have to apply it at a number of radial locations, a number of span-wise locations on the wing. Rather than changing the span-wise location, we change the theta naught. Okay. So for example, you don't want to apply theta naught equal to 0, which is a one wingtip, because what happens is this goes to 0, this goes to 0, so you don't get anything out of it. Then you just get alpha equal to alpha naught, but CL equal to 2 pi times alpha minus alpha naught, you get 0 left, nothing of value. Same way, you do not want to use pi because sine of n pi is 0, sine of n pi is 0. So we want to exclude theta equal to 0 and theta equal to pi. Also, because information is symmetric, whatever the left wing is doing is what the right wing is going. We don't need to do all the way from 0 to pi. We could just take 1/2 of the wing, 0 to pi over 2. Then you can, the other side of the wing is going to do the same thing. So if you keep two terms here, number 1 and number 3, then you can divide the 0 to 90 degrees, which is 0 to pi over 2, into 45 degrees and 90 degrees. That means you can apply this equation when theta naught equal to 45 degrees, when theta naught equal to 90 degrees. If you keep 3 terms, 1, 3, 5, then you can say theta naught equal to 30 degrees, 60 degrees, 90 degrees. So equally spaced theta naught, depending on how many terms you want to keep in this series. It turns out typically 1 to 5 terms is enough. In homework problems, exams, we will keep only 2 terms just to make life a little bit easier. What happens if you just keep 1 term? Then you just get 1 term, 2bv infinity times sine of theta. That's nothing more than our elliptical loading. Remember, our elliptical loading gamma was some constant times sine of theta. So we get back our elliptical loading with 1 term. So the other terms deal with how much we are deviating from an elliptically loaded situation. So let's go back and see the elliptical loading gamma. This is the elliptical loading. It just has got a one term, which is sine of n theta. So here for a general wing, we have several terms. So it's an infinite series, but we are going to keep only a few terms, and then we are going to solve this equation. So later on, we are going to do some worked out examples to show you how to set up this equation and how to solve it. So if you're doing computer program, you will keep maybe 10 terms. That's plenty good enough. If you're doing by hand, just keep 2 terms, n equal to 1 and n equal to 3. So pick 2 theta naught values, 45 degrees and 90 degrees. That's sufficient. So anywhere from 2 terms to 10 terms can be kept. So we are going to apply this equation. For example, if it's 3 terms, then we'll apply it 30 degrees, 60 degrees, 90 degrees. If it's just 2 terms, we will set theta naught equal to 45 degrees and 90 degrees. So equally spaced values. So if you have n terms, then it will be pi over 2 divided times n. So depending on what is n, that's the increment by which you go. So our website already has a MATLAB code, and we can solve this problem. Right now, let's look at what happens to the downwash, what happens to the induced drag. So using this series that we assumed, if you integrate it, rho infinity times v infinity times gamma, that's the lift per unit span. So if you integrate it from wingtip to wingtip, from minus b over 2 to plus b over 2, that means you're integrating from theta equal to 0, which is one wingtip, to theta equal to pi, which is the other wingtip. So if you integrate it, you will get a very simple expression that requires only the first term. If you look at the L prime times alpha I, which is this term we have already integrated it, alpha I. L prime is rho v infinity times gamma, so multiply this by rho v infinity times this expression. Then you get double series, an sine n theta times nan sine n theta. So you're going to get an squared in general. So integrating for the drag for the whole wing after some algebra, I'm skipping some of the algebra here. It's given in the book. You could do it. It just takes some time. This is the induced drag that we get. If you note the leading term here, this is the elliptical loading term. Elliptical wing has got the lowest induced drag. All these extra terms, all of them are positive. They increase the drag. So the more you deviate from an elliptically loaded wing, the larger these numbers are, A3, A5, A7, etc. A1 still dominates, the first term, but these give you non-zero contributions, therefore you get a high drag. So the role of a designer is to reduce this A3, A5 by tapering the wing, twisting the wing, try to optimize the wing. So this is what you would do if you work as an aerodynamicist at Boeing or Airbus or Embraer or Bombardier or at Gulfstream or at Embraer. So we are going to now go to a worked out example. So it's a tapered wing. The root chord is 2.381. The tip chord is 0.953 feet. So we're going to use cambered airfoils. That means it's got an alpha naught. So the alpha naught is minus 1.2 degrees. Alpha is given 4 degrees. The wing is untwisted, therefore everywhere all over the wing you're using the same alpha. In real world, near the root you will have a high alpha, so the nose of the airfoil is pointed towards the sky. Near the tip it may even have a negative alpha, so the nose of the tip airfoil is rotated downwards. So in between you have a twisted wing, pointing upward to pointing downward. So from root to tip, you have a continuously twisted wing. But we are going to make it simple. We are going to assume the wing is untwisted. This is our A naught. A naught is 2 pi. So we are going to solve this by hand. We are just going to keep two terms and we are going to solve it. So I'm going to show you how this is done in the remaining pages. Then in the next video, we will bring up the MATLAB code from our website and try to run this case and see what we get. All right? Okay. So start with this equation. This is for the general equation for the downwash. Now we are going to keep only two terms. Terms are A1 and A3. So we need only two terms, so theta naught need to have just two values. First time we will apply all over the equation theta naught equal to 45 degrees. We need to pick the correct chord at that particular location corresponding to 45 degrees. Because as theta naught changes, y naught is changing. Because it's a tapered wing, the chord is going to change. Span is a constant. Lift curve slope is a constant. So we don't need to worry about B and A naught, but the chord will change. So B is 15 feet. A naught is 2 pi. So we need to find C at y equal to, for the first time, theta naught equal to 45 degrees. Second time, we need to do it at theta naught equal to 90 degrees. That means since our wing is a trapezoidal plan form, it's got a linear taper between this value at the root and this value at the tip. So it's linearly varying from root to tip. So that linear variation, we can fit this as this. Chord at any y location is chord at the root minus chord at the tip minus chord at the root by semi-span times y naught. Okay. So let's say y naught is 0. That means you're right on the root. Then this whole term will disappear. Then you'll get the chord equal to chord at the root, which is 2.381 feet. Let's say y naught is all the way at the tip, so it is a semi-span. Then that semi-span and this semi-span will cancel out. This should be really C root minus C tip. This should be really be a plus. I'm sorry. Okay. But if y naught is minus of semi-span, because remember we are looking at the y naught equal to minus of v over 2 cosine theta naught. So when theta naught equal to pi, this will become, when theta naught equal to 0, this will become, when theta naught equal to 90 degrees, theta naught equal to 45 degrees. It's a negative value. So for negative y naught, like a negative semi-span, negative of negative is plus. C root and C root will cancel. You will get a C tip. This works only for linear wings. Okay. If it's a constant plan form, we just have one chord. Nothing is changing along the span. So now you apply this equation. First up to theta equal to 90 degrees. So A1 times sine of 90 degrees. You get A1. A3 times sine of 370 degrees is minus 1, so you get a minus 1. Here you get 1 times A1 times sine of 90 degrees by sine of 90 degrees, so you get 1 times A1. 3 times A3 times sine of 270 degrees by sine of 90 degrees is minus 1, so you get a minus 3. Minus this 3 comes from this n. This minus comes because sine of 270 degrees is negative, sine of 90 degrees is positive. What is this 4.016? It's just a 4 times b times a naught times c at the root. So when you just plug in the c at the root, which is 2.381, then you get this 4.016. In the second equation, C is at 45 degrees. Theta is 45 degrees. So the chord from this linear interpolation is found as 1.298 feet. So that's the chord we'll have to put in. So this number gets bigger. Smaller chord, bigger number. So sine of 45 degrees is 0.707. Sine of 100 to the 35 degrees is also sine 707. So this comes from the first term in here. Sine of 45 will cancel out, so you'll get 1 times A1. Sine of 135 and sine of 45 are same, so they will cancel out. You'll get 3 times A3. So if you group these terms properly, you get this equation. So you get two equations for A1 and A3. This is the first equation. This is the second equation. Note that alpha should be in radians. Don't use degrees. I have given you 4 degrees. So convert immediately the 4 degrees into radians. This is minus of minus 1.2. So 4 plus 5, 1.2 is 5.2 degrees. So 5.2 degrees must be converted into radians. Okay. So alpha minus alpha naught is in radian. So solve this 2 by 2 system of equation. Then you'll get this as the answer. Okay. A1 and A3. As soon as you get these two terms, CL for the whole wing is given in here, 0.4613. CD for the whole wing is, just plug in for A3, this number, plug in for A1, this number, crunch it out, you get this number. Okay. CL we have already found it, so for CL squared goes here, pi. AR is the aspect ratio. Aspect ratio of the wing is span squared divided by the wing area. Okay. So you need to know the aspect ratio of the wing. You can find the wing area because this is the root chord, this is the tip chord. Take the average of the two, that's the average chord, multiplied by the span, which is 15 feet, that's the wing area. Okay. So span squared, which is 15 feet squared times 15 feet, 225 feet squared is the span squared, divided by the wing area is going to be your aspect ratio. So you get this as your induced drag. So we are going to stop this video here. In our next video, we are going to run the MATLAB code at our website. Then I'm going to show you how close we get to these numbers and how to interpret the MATLAB program output. So we're going to stop our recording.